Hello, good afternoon. So we'll start the class after 4 5 minutes. So good afternoon, everyone. Does my slides are visible? Someone please tell. So someone please confirm my slides are visible. Yes or no? Hello. I think my screen is visible. So let's start today's live session. So before start, I am introduce about myself. So I am Povin Maiti, teaching assistant of this course. So the course name is Introduction to Polymer Science and course instructor Professor Divakar Dhara. So earlier classes we are solving some problem related polymer synthesis. Then we talk about that how we can synthesize the polymer. Then today's classes we are mainly solving some problem like related to the how we can characterize the polymer, how we can characterize its molecular weights, its property, all of like this. So to characterization of polymers, pretty my screen are visible, right?
Yes, sir, it is visible.
Yeah, thank you. So earlier classes we are solving some problem related to that polymer synthesis and its application, how we can synthesize the polymer. So today's classes we are mainly focusing some problem where we can characterize how we can characterize the polymer. What are the techniques we can characterize like that. So the first question was the value of osmotic pressure. So before start the characterization of polymer, so just brief introduction how we can characterize a polymers. Like if if we do the free radical polymerization, so like in free radical, generally the double bond converted into the single bond, right? Or we're not doing like condensation polymerization, then there's some functional group involved. Like if you're doing like C double OH, like simple, if you make onto ester, C double OH functional group make your ester group, like you are getting R G O R like that. So how we can characterize this? So if you just characterize that from the monomer to polymer conversion, then you can characterize by IR spectroscopy for these functional group detections. So like acid and alcohol, that IR spectroscopy are different. When it become the ester, so that IR become different. Also we can characterize this polymer by NMR spectroscopy. So NMR spectroscopy will be like this. So what can we get from the NMR spectroscopy? Like IR only tells about the functional group, but in NMR spectroscopy we can detect.
Number of hydrogens, carbon
Yes.
present in the polymer chain.
So you can detect that number of hydrogen present and number of carbon present. So like if you do like a polymer sample, like simple earlier classes I am talking about some ring opening polymerization or something like this. So if you do that polymerization of ring opening polymerization, like if you have some group will be like this. So if we do like this, so it will become CH2. So like your glycine molecule, so how it will be look like your glycine? So glycine will be look like, so this is will be your NH2, and this is will be your COOH, right? So like when to make that polyglycine, so we are making like a monomer like this. So where it will be like CH2, it will be C double bond O, and here it will be your nitrogen, it will be NH, C double bond O coming. So if you make like such polymer, so this monomer is called that NCA, N carboxy anhydride, so that it is called glycine NCA. So if you any like any initiator is coming like RNH2, we are giving the general example. So after this RNH2 coming, so it will be this nucleophile will be attack this carbonyl, and from here CO2 will be released. So it will be C double bond O CH2 NH. In every repeating unit we are getting CH2 NH. Sorry, C double bond O. Like this will be a repeating unit, right? If you're making the polyglycine, so this will be this C double bond O. This will be CH2, and this will be your NH. So if you pointer it. So this C double bond O, which will be connected with your initiator. So like this will be your initiator C double bond O. So this will be again NH, and this will be your R. Like this, and it will be to the power n. Like this number of molecules are repeated, and this will your n group. So which are present in the end and act as an initiator. So this will be your n group. Right? Did you understand like this up to this? Hello.
Yes, sir.
So now you want to take that NMR of this sample. So what we are getting? So from NMR, so first we will take that NMR of that our monomer. if you take the NMR of the monomer, so in NMR, if you look doing that proton NMR, so in proton NMR, in the monomers, what group are present? One NH is present and one CH2 is present, right? So we are getting the NMR will be like, so the your CH2, which is coming around 4 or something, because there will be some carbonyl beside that this group, so that one photon peak you are coming around the CH2 peak here, and amides which are more decelerated, so it will be coming around 7 or 8 like that. So this will be amide peak NH, and this will be your CH2 peak, right? And we are getting a single peak, like not broad, it will be like single peak. So like similar sample, if you do that polymer, so in polymer now there will be some RNH group is present as a N group, so that maybe this R group are coming in the very lower sides, maybe, so it will be start 0, so it will be around 4, it will be around 10. So now this that CH2 position of this after polymerization, so now we are doing the polymerization of NMR of polymerization, polymer NMR spectra. So you do like this, so this CH2 peak is almost remain same, but now the peak will be like more broader, so you are getting that broad spectra of this, and here this amide also you are getting broad spectra, and you are getting some initiator like this N group peak also. So if there will be N group, like if you are getting N group benzene, like if you are benzyl amine, so it will be NH2. If the N group will be like this benzyl amine, so it will be coming around, benzyl group is coming around 7 or 8 like that, so the benzyl proton will be coming here, sorry, so it will be 7 or 8 near about like this. So this will be your N group proton, and this will be your polymer proton. So also from that NMR characteristic we can calculate the degree of polymerization, like that how much polymer, uh, how much that repeating unit present into the polymer. So like this N group there will be benzylamine, so in benzylamine there will be 5 proton, right, for benzene group, and from this 5 proton if you are getting this broad peak around, you are getting this broad peak, let's say 100. So in 100, that means that your N group will be, there will be 5 proton, and that this broad peak have that 100 hydrogen. But in this region, how many CH2 is there? So there will be 2 CH2. So total 100 hydrogen means how many CH2 are repeating? It will be 50, right? It will be half, because every hydrogen, the 2 hydrogens, 1 CH2 group. So like, so here the repeating unit will be, so this will be 100 times, so there will be CH2, so that will be means 50. So the repeating unit should be 50. So like this N group analysis, like what N group are present into a molecule, we can characterize the degree of polymerization of the polymer. Did you understand? Also, like if your N group will be like, if there will be N group like methyl, so if you like, you have reacted this polymer with the methylamine, so now this methyl will be coming here. So let's say that methyl, the methyl means there will be 3 proton is here, and according to this 3 proton, we are getting 100 proton of this. So also that degree of polymerization will be 50 for this molecule. So you have to integrate this N group like the integrated value should be 3, and from here we are getting 100 of the integration value at the region of this CH2, so it will be coming around dp50, and this NH should be coming 50 because only one NH proton is there. So did you understand how we can get an idea about degree of polymerization from that NMR spectra? Hello? Hello? Preeti, did get someone?
There is a break in voice, sir.
What? What I did not understand. Hello?
Yes, sir. Tell me. There was a break in voice, sir.
Okay. So did you understand that how we can calculate? Now it will be okay.
Ah, yes, sir.
So did you understand how we can get that molecular weight?
Ah, yeah,
Not
yes,
molecular,
sir.
the degree of
The
polymerization of
degree
that
of
polymer.
yes,
Yeah.
yes, sir. Of repeating unit.
Yes.
Ah,
So
yes.
repeating unit we can calculate, and from that repeating unit, so if there will be 50 repeating unit, so now we know that how many that monomer molecular weight, like that repeating unit molecular weight. So if there will be 50 repeating unit and that molecular weight of this, you let's say it will be 50. So now we can also calculate that molecular weight of that polymer, right? Because we know that repeating unit molecular weight. Now you know the degree of polymerization also. Now we can calculate that molecular weight, right?
Yes, sir.
Yeah. So like there will be several techniques that we can characterize the polymer after polymerization. Like this will be like NMR, like in IR spectroscopy you know just about the functional group. If there will be some functional group changes, like from here there will be two carbonyl group is convert into amide group. So the functional group are changes. So from that monomer to polymer conversion you can characterize that this monomer functional group are not still are present into the polymer. All our polymers will be happened. Like in condensation polymerization also from that acid alcohol to we are getting ester. So by functional group detection we can get an idea that that polymer is converted. But if you want to know that about the degree of polymerization of that polymer, so you have to do the NMR spectra of this sample, so you can get an idea about that degree of polymerizations and molecular weight. And if you want to know that polymer molecular weight, so which are NMR solvent are not possible or where we cannot detect that n group analysis, by the n group analysis, then we can do that GPC of that sample. From there we can also then characterize the molecular weight. So this GPC and all of this I will tell in the next. So now the first question is coming, the value of osmotic pressure are given for a polymer sample PMMA which molecular weight is 20,000 in acetonitrile at 37 degrees centigrade. So you have to find out that osmotic pressure. So what are the equation for the osmotic pressure? The osmotic pressure is pi equal to CRT by M, right? So here your concentration are given 2 gram per dl inverse. So now we have to that R is a constant. The temperature also given 37 degrees centigrade and molecular weight also given 20,000. So now we can put, so 2 into here R will be 0.82 if we are making this that unit same. Then this Mn value we put, and temperature it will be in Kelvin. So like Kelvin, if you convert degree centigrade to Kelvin, so it will be 37 plus 273. So it will come 310. Now you can put here and you can calculate easily that osmotic pressure, right? So this will be that solution. So the concentration 2 into 0.82 if you put, and temperature 310 Kelvin and divided by molecular weight, we are getting this value 0.2542 atmospheric pressure. Okay. So now the next question is select the correct statement of the dynamic light scattering measurement of a polymer. So what is DLS measurement? So in DLS measurement will be like this will be your maybe the DLS instrument. So from here there will be some space where we can put our sample. Like you can put your sample in a cuvette. So in cuvette, so there will be some light pass. So DLS means the dynamic light scattering means, so your sample have some volume, right? When into the solution, so it will be some value. So now light, when the light will be pass, if there will be smaller molecule and if there will be larger molecule. So light scattering from the smaller molecule and from the larger molecule will be different, right? So when the light will be coming here, maybe this light scattering will be, after scattering the light will be like this. But when there will be larger molecule, so light will be coming here and that scattering will be different. So from this light scattering value we can calculate. So like this an example. So from the laser the light is coming into the sample. So from there, depending upon the size of the sample, so light will be scattered from that sample, and from the detector we can get an idea, correlate and plot, and from there we can get a size distribution plot. So for DLS measurement we can detect the size of that your sample. So if it is the polymer, so polymers are mainly little bit higher size as compared to that smaller molecule. So you can easily get that size of that polymer. So here mainly the size of the polymers are mainly that its hydrodynamic radius, means in which solvent it will be present, that hydrodynamic volume we can get. So from that DLS measurement we are getting that only hydrodynamic volume. So and this volume we can get from that the radius of this. So which will be that correct answer? So what we can get from the DLS measurement, like radius of gyration, hydrodynamic radius, RG and RH both, the both of radius of gyration and hydrodynamic radius, or none of the above. Which should be right answer? So here only we can detect that volume, hydrodynamic volume, and that volume we can get an idea about that radius, not that radius of gyration. So this should be the right answer. The hydrodynamic radius we can detect from the DLS measurement. So if you saw that equation of the DLS measurement also, so from the Stokes it will follow this equation, Stokes-Einstein law, that the R is equal to KT 6 pi eta 0 into D, that the R is that radius of hypothetical sphere or hydrodynamic radius we can call it. Now the next question was that two ends of the polymer molecule of a sample nylon 6 are capped with COOH group. Like a nylon 6 polymer, so where the both the side will be COOH is present. 1 minute. Hello? Our class is I'm into PowerPoint. Electrode, here it is that now I am audible, yes. So nylon 6, where both the sides COOH group are present of this 8 gram of sample, is found content its 8.10 to a minus 3 mole of COOH groups by titration with the alcoholic KOH. Now you have to calculate the molecular weight. So, so you have to find out the molecular weight. So now the weight is given and your mole is given. So now when you want to calculate the molarity of any solution or moles of anything, so mole will be, it will be like is your weight divided by molecular weight, right?
Yes, sir. Molarity.
Yeah. So now what do you find out the molecular weight? So now molecular weight will be, so your weight, so now MW if you calculate them, so it will be weight by your moles, right? So now it will be tell that your when you like titration, so in titration what we get, your acid will be titrated with the potassium hydroxide, so both the acid will be get titrated, but in one polymer sample how many COOH group is present? Two COOH group is present, and what amount we are getting, the COOH concentration is 8.8 into 10 to the minus 3. So one polymer change means 2 COOH. So when we're talking about polymer sample, how many moles is present? So it will be divided by 2. So like one polymer sample, there will be 2 COOH group, and the total concentration of COOH group will be 8 into 10 to the minus 3. So that polymer sample concentration, the polymer concentration will be, so it will be 8 into 10 to the minus 3 divided by 2, right? So did you get my point?
Yes, sir.
So now the polymer concentration is 4 into 10 to the minus 3, right? So now we can divide it. So 8 divided by, so 8 is this one, divided by 4 into 10 to the minus 3. So how the 4 will be multiplied 2. So the molecular weight into 2 into 10 to the 3, like 2000, right? If there will be one COOH group, then the concentration will be the similar to that the polymer sample concentration. But if there will be two COOH group, and from that titration we can only get an idea about that COOH group. So then we have to divide it, that concentration of COOH group, to get that polymer concentration. It should be divided by 2. How many functional group are there? So that will be we have to divide that to get the polymer sample concentration, right? So we can get that molecular weight of the polymer. So now next question was, a scientist wants to determine the weight average molecular weight of a polystyrene sample anticipated to have the molecular weight value around 3 into 10 to the power 5, 6 into 10 to the power 5 gram per mole inverse. Which of the following methods should be employed by him? So like a similar polymer sample, and which of the molecular weight value are different. like one is the 3 into 10 to the power 5 and one is the 6 into 10 to the power 5. So which technique we can use to get? So here mainly what it tells that polymer which have that dispersity of the polymers are different. So by end group analysis we cannot calculate the dispersity of the polymer by NMR studies also. So light scattering only tell about that size of that polymer, osmotic pressure only give that polymer exact molecular weight. So that, and viscosity measurement, so we can detect the viscosity, but to know about that the exact molecular weight of that polymer, so we have to do the light scattering method. Now the next question is that from the theta equal to 0 extrapolated line in the Zeeman plot in the formation information can be obtained about MW, A2, MWRG, MWRH, A2RG. So if you see the equation of this theta equal to 0 for the Zeeman, so as per the following equation you get an idea about that your MW value and your A2 value, not this RH and RG value. Now the next question, which of the following methods can be applied to determine complete molar mass distribution of the polymer? So when you want to get the mass distribution like dispersity of the polymer sample, so you have chosen a technique we called it is GPC. So GPC, and it's also called ACC, size exclusion chromatography or gel permeation chromatography. So here what we, so like one GPC instrument will be like this. So here will be some chamber, so where we can inject our polymer sample, and this polymer sample goes into this, so this will be our column, and from this column the polymer sample passes through a column, and then we get from the detector how the distribution will be like. We are getting a peak. So like so here mainly that like in GPC in that column, so the column will be look like this. So the column will be making with that some polymers, and in that polymer there will be some pores are in between. So and during, so in that pore, so when your sample is coming here and passing through this column, so which of that smaller size, so it will be goes into this pore. Like if there will be pore, the smaller size molecular weight are goes into that pore, but the larger size will be coming passing through the column first. So when you draw that with the time, if you get the plot that how it will be coming, so you do a plot like this when there will be larger molecular weight. So if the time will be like this, so when you do the larger molecular weight, so it will be coming fast earlier, and when there will be lower molecular weight, it will be coming later, because the lower molecular weight which will be lower in size and it will be goes into the spore, so it will be take times. So from there we can calculate that polymer molecular weight. So if you have this some standard sample, so from standard sample you know that molecular weight of that polymer, so you plot it like for 20,000 that timing will be like say 5 minutes. When there will be 10,000 the time will be maybe 2 minutes. If there will be 5,000 the time will be like 3 like 1 minute. Oh sorry, so time will be reversed. So like more molecular weight, that 20,000 time will be 1, the 5,000 the time will be let's say 3 minutes, and 5,000 molecular weight that time will be 5 minutes. So it will be 5k molecular weight, it will be 10k, and it will be 20k. So if you know that standard polymer sample, the curve will be look like this. So now your unknown polymer sample, if you inject here, so maybe you are getting point somewhere here. So it between 5,000 and 10,000. So from this plot, if we like if with the timing, if we extrapolate it, and from that software you can calculate that exact molecular weight of that sample. So from that known sample solution, if you get and plot, and if you inject that unknown solution there, if you get a point there, or if you get a distribution plot there, and from this distribution plot you can get an idea about your unknown polymer sample, how much molecular weight of this. So from this GPC studies, so there will be also know about that PDI of the polymer. So PDI means that polydispersity index. So what the polydispersity index, it will be suggest that your MW
by
by
MN.
mm. Yeah. So you can get an idea when there will be some broad peak. So if you are getting two peak, like one polymer sample have that this peak, and another polymer sample have the the peak will be like this, like similar. The it will be little broader. So that broader peak suggests that the polymer sample have the PDI will be high, and that more steep peak suggests the polymer sample PDI will be low. So when that MW and MN will be 1, so that means their PDI will be 1, so there will be more steep plot. When there will be 1.2 or 1.3, the PDI getting more broad and broad. So if there will be more than 2, so now there will be like bimodal distribution we are getting, like this type of plot. So that time it will be suggest that there will be maybe that two two polymers are present which have the different molecular weight, not a single polymer chain, like that. So from that GPC study we can get an idea about that polymer molecular weight. Also we can get an idea about that your PDI of the polymer, so how much polydispersity index we can get. And from that, and PDI is very much important to get detect about that properties of the polymer. So when that PDI will be very low, like steep PDI will be low around 1, so that property will be much better as compared to when there will be PDI will be high, when there will be broad spectra, because the broad spectra means so there will be various chains which have the different molecular weight, like that. And smaller PDI, that means there will be similar chain length are present, and when there will be similar chain length are present, so that time the property are of this polymer are very much better, because that when there will be similar chain length, so that crystallinity of the polymer will be better, so the thermal stability all of these properties will be better. And when there will be like small chain and larger chain are present, so that thermal stability of that polymer are not better. So like that GPC studies or size exclusion chromatography studies, we can get an idea about that distribution of the polymers, and also get an idea about its molecular weight. So here the question is that which of the following methods we apply that determine complete molar mass distribution of the polymer sample. So if you want to get the distribution of the polymer, so you have to choose that GPC measurement. Okay. So now the next question is generated like in the multi-TOS MS polymer. So multi is also a studies where we can get an idea about polymer molecular weight. So how multi will be look like this? So multi means is a mass spectroscopy, and what the mass spectroscopy doing like this, when if you give your polymer sample, like a polymer sample will be like this, when you passes through a multi, so it will be chopped your polymers, like it will be cut in various sizes. So like if there will be 20 repeating units, so there will be 20 chop, 20 times it will be cut your polymer, and from there we are get and peak like your higher distribution, like the peak will be like this, then will be like this, it will get, so that highest peak suggests, so that will be suggest that uh, so that if the dp will be around 20, so highest peak will be suggest that how many chopped that will be maximum possible of this polymer, and then the distribution will be lower and lower, the size will be lower and lower like this. So from here we can also know about that how much difference between these two, like if so multi also tells about that your repeating unit structure, like if your polymer, like if you have a sample and your polymer, there will be two monomer are present. So after chopping, so the maybe we tells that a have that monomer mass is around, repeating unit mass is 100, and b is repeating mass is 200, and there will be total 20 molecules present, so a will be 10 and b will be 10, let's say. So now we can so multi studies we can also get an idea about that how a and b are arranged into the polymers, like if a, so if this that overall a and b, so now the next which are connected with this, if this difference is 200, the molecular weight difference between this larger peak and this peak, so it will suggest that, so if this first one is the a, so the next one should be b, and if the difference will be 100, so that will suggest that a will be connected with that a, not with that b, so that we can get an idea about that how the repeating unit and how the arrangement of this repeating unit of this polymer into that polymer sample, so you can get an idea. So mainly for that protein sample, which is the polypeptide sample, so polypeptide sample, that sequence of the polymer are very much important. So for this reason we can do that multi analysis, and we can get an idea that which amino acids are connecting, like after, if it will start with the glycine, so after glycine what amino acid present, like alanine or something, proline or like that. So from that how many molecular weight difference between these two peak, we can get an idea about that which are next monomer beside the first monomer one, we can get an idea about that. So for the multimatrix we are generally use some aromatic organic acids we are using. So now the NMR is not used for the determination one of the following polymer attributes. Identify the, so from NMR studies,
Conversion.
the conversion we can calculate, like if you do that crude NMR spectra.
Mm.
So crude NMR spectra means where both that polymer and both the monomer are present. Like
Okay.
your polymer peak will be like this, and your monomer peak, which will be more steep, right? So it will be like this. And if these two peaks are like after that polymers, sometimes the peaks are getting little shifted. So now in the crude monomer mixture, you will get that monomer peak also. You get an idea about the polymer peak also. And now you integrate that value. maybe this will be 20% and this will be 80%. So from there we can get an idea that there will be 20% monomer are remain into that polymers. So and 80% conversion are happened. So from
Molar
that
mass distribution.
right, yeah. So we can get an idea of conversion of polymer also. So copolymer composition, like if you have the two monomer like A and B, so like A peak is coming here and B peak is coming here. So you can get an idea about that how much A and how much B is present into that NMR. So you can get an idea about the copolymer composition. So nature of tacticity sometimes also detected by the polymer. So like when there will be some isotactic polymer that the peak shifting is different, when there will be some like atactic polymer, maybe that peak will be some different. That from that peak analysis you can get an idea about the tacticity of the polymer. So but that mass distribution, like how much PDI you cannot get from this in mass studies. To get that mass distribution, we get that GPC. So mass distribution means that PDI of the polymer we cannot get. So from animal we can get only the molecular weight, not that distribution, how that molecular weight are distributed into the polymers we cannot get from that animal studies. Now the next question was that will four monodisperse polymer sample of same molecular weight as determined by light scattering have the different shapes. In, in THF, it will be coil, extended coil, rod, and sphere. If these four samples are passed through a GPC column under the experimental condition, the column solvent temperature, flow rate, and detector position, what would be the order of elution be assumed to the column can be separated all four polymers. So how GPC can detect that polymers? So it will be only detect by its size, right? So how the polymer size will be look like? If the size will be larger, so from the size it can detect the polymer sample. If the size will be larger, it will be, if for the polymer sample, the so that will be depend that hydrodynamic volume of that polymer sample, how we can comes out from this there. And for that normal column, if we talk about that how it will be look like, so so that depend on the size. If the size will be very small, so that will become fast, and if the size will be higher, so that will become later. So by only that size detection we can get an idea that how it will be coming. So if you talks about the size of the rods, extended coil and sphere, when there will be size, that rod means, so they have no coiling structure, so it will be coming fast, the size will be lowest there. So when there will be extended coil, so that size will be little bigger. When there will be more coil, the size will be more bigger. When there will be sphere, so that will be much more bigger. So from there we can the illusion separation of will be that rod will be fast, then extended coil, then that will be sphere. So like the answer would be like this. So in GPC elution happens by that hydrodynamic size. The largest sites get eluted fast and the lowest in the last. So for a given molecular weight, the order of the size in a common solvent and in the same temperature, the rod, then extended coil, then the sphere. So the order will be elution will be the same with that size. Sorry. So here the mainly that GPC will be separated by its hydrodynamic volume. So if you compare that volume of the sphere and volume of some extended coil, so which have the larger volume? So sphere will be that lowest volume, right? When something becomes sphere due to that, to making that surface tension very low, so that sphere will be the most lower size as compared to this. That volume size will be lower as compared to the rod, extended coil and coil. So that sphere will be last because that the GPC which of the lower size that goes into this column pores, and which are the larger size, so that will be coming first. So for this reason the rod will be coming first because it have the larger in hydrodynamic volume as compared to that sphere, extended coil and coil. Now the next question was from the following plot determine the molecular conformation of the sample. If the plot of log Ra versus log Mw will be straight line, so it will be that if you do that log Rg versus that molecular weight difference, so it will be some intercept plus log M, so it will be follow the straight line. So from there it will be suggest that it will be that rigid rod structure of the polymer sample. So do you have any problem up to this?
No, sir.
Okay. So today's is up to this. So then we'll meet in the next week. Okay.
Okay, sir. Thank you.